Okay, so beginning now. So today we are going to talk about the matrix, okay? Matrix, displacement method. Generally, some class they would begin with the matrix force method, but that's a force method written in terms of matrix. It's nothing much different from the force method that you had your pain in structural analysis number 1, but it is only written in terms of matrix. And by and large, that method is not very useful to computer programming, because if you're talking about a force method, you need to create your compatibility equations from the primary structure. The computer program cannot create the primary structure by itself, so it has to be done by hand. So to have the matrix method that partially done by hand, it is not very useful. So I sort of ditch that away and begin everything with the matrix displacement method. Okay, so you don't have to wonder why you don't have this method in your class, because I don't think nobody in this world uses that anymore. Okay. Now, if you can go back to your basic equation from, your days of mechanics, your days of physics, when you have a spring in the physics, you always have this equation, right? It's F equals Kx. Or I can say in terms of structure, we generally prefer to write in terms of F equals to Kd. X and D they are essentially the same thing, displacement or deformation of the structure. Okay. Now, of course, F is the force, X is the displacement or deformation. Okay. So you should look at this simple equation and see the simple relationship between the force and the displacement. That is K. Okay. K is, of course, stiffness. And because you can see from this simple equation that stiffness relates force to the deformation of the structure, that is why it is the most important property of the structure itself. That is why I always emphasize on the fact that you should be able to identify stiffness, okay, whether it's in the continuous beams or in the frames. Okay, a failure to identify stiffness means that you could never really get down to the bottom to identify the relationship between force and deformation. Okay, so stiffness is what we need. And in matrix displacement method, of course, you can guess now that we can write force, we can write deformation, and we can write stiffness in terms of matrix. Okay, now stiffness is something that you truly need to understand, because I've been involved with the making of many Thai standards, and they always try to find a Thai word for every conceivable English word that relates to a structure. Like force, displacement, they all have the Thai words for it, but for stiffness, they can't. They try to match some Thai words with the word stiffness, and in the end, they don't really convey the true meaning of stiffness, because stiffness is the quality that tells you how much your structure is going to deform under the force, right? Just like what this equation says. So in the end, they settle with the word stiffness. So stiffness in English is stiffness, and in Thai is also stiffness. There is no other Thai word that can replace stiffness, okay? Because mark my words, it's the quality that relates deformation the force. Okay, and now you know, you can guess that depending on the system, you should always have the stiffness that corresponds to the force. For example, if we're talking about the thrust, the stiffness should be about the deformation of the thrust or the two force member. If you move on to the beam, the stiffness should be about, you know, the rotation of the joint. And if we're talking about the beam column or the frames, now the stiffness should represent both the axial deformation and the rotation. All right, so with that said, before we are going into the stiffness itself, let me try to review this slightly bit for you. Let me draw a picture of a truss. Okay. Now let's put the simple support here. Now you guys should recall, I don't even have to do this because truss is you know, the very basic fundamental structure that you learn from statics. But because you still have the bad habit of learning from primary school and high school that, you know, once the exam is over, you throw everything away. Well, you know, it will take some time before you can grow up from that. So I probably think that you forget everything about this. So truss is a two force member. So that means there is no rotation involved. So when we talk about degree of freedom of the truss member, yes, we still look at the joints, but there is no rotation. Okay, so that means this joint is free to move in X and Y direction. With that said, you probably can see now that each joint can be represented by 2 degrees of freedom, the movement in X and in Y direction. Okay, so we have 2 for one joint, 2 for this joint, and then 2. So we have 6. When you look at this joint, it's a support. So there is no degree of freedom because it's a hinge. So there's no movement in any direction. And in this, it's a roller. So it's free to move in horizontal direction, but not in vertical direction. So in this particular system, you can see that you have the 7 degrees of freedom. Okay. And because we are now in the metric displacement method, so it is the displacement method. So we need to identify degree of freedom before we solve any problem. Okay. And ladies and gentlemen, failure to identify degree of freedom means that you don't know what structure you're dealing with. You don't talk to your structure. And when you don't talk to your structure, you get 0. Okay. Failure to identify degree of freedom is your favorite word, fatal. So again, just like the previous problems that you've been dealing with before, if you begin with the wrong degree of freedom, the rest is garbage. Okay, so get this fundamental right before we begin anything. Is that crystal clear? Okay, you can try to go back and try to identify, say, more structure. For example, I can show you one more. If I give you some sort of a truss like this, perhaps. Can you count the degree of freedom? Suppose I'm going to be the one who counts, right? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So this system clearly has 10 degrees of freedom. Okay? So it's time to get into our fundamental now. Let me have a minute to locate what we are going to have today. You guys have any question? Remember, if you don't get degree of freedom right, the rest is useless. Okay, so try as you may on working on the metrics and stuff, but if you don't get the fundamental right, no use. Okay. All right. Oh, it's a long way from here. Okay. So generally we will talk about the trust, right? Okay. I am not going to get into the matrix displacement for beams or for anything. Okay. Just the introduction to matrix displacement method as a whole. So we're going to look at the trust. So could you please look at your document that I gave you yesterday? It's called a supplement for the matrix displacement. Okay. I don't like writing in here, but you know, you guys can use this sheet. Okay. And I'm just going to reverse back to my good note perhaps, but let's try. Oops. Oh, geez. Okay. So let's look at the one trust member. Okay. I think perhaps I can do this. Oh, I wouldn't. Okay. And I can write. Excellent. Okay. Maybe it's the wrong button after all. So, all right. Let's say this has the length L, and I call, you know, because the trust member is a length. So let me call this one node number 1 and that node number 2. So when we talk about that, you think maybe we should have the typical direction for this. That should be the XY system. Okay. You know, the official name of the XY system, can you recall? It's called Cartesian, you know, coordinate system. Okay. And in node number 1, if it's free to move, I can say at node number 1, I can have the force at node number 1 and displacement at node number 1. And likewise, in node number 2, I can have force at node number 2 and displacement at node number 2. Now, generally, we should always identify which member we are dealing with, and we can do that by adding the superscript on this. So this is any member I, so I'm just going to add the superscript I to the force and displacement. The force and displacement here. So now you know this F1 is the force at node 1 of member I, and D1 here is displacement at node 1 of member I, and likewise for node number 2. Okay. So now in order to develop the relationship between force and displacement, I need to look at this again, and I should try to add the support here on the right first. Okay, I should take off the glass as well because I can't see very well. So right here, we will consider D1 of this member I first. And because I add the support at node number 2, so that means D2 is equal to 0, okay? D2 of member I. All right, and if you can recall, if I apply force here, F1, I can calculate displacement D1, okay? So to avoid confusion, I'm gonna stop writing the superscript I for the time being, but you guys should know that it is always there. So D1, by using your basic relationship from Hooke's law, you can see that the displacement is equal to F1 multiplied by L over AE, or PL over AE, but in term it is now represented in terms of F instead. Okay, so from this I can also write the force F1 equals AE over L multiplied by D1. All right. And look at this free body diagram. You should know by now, but because we are going to use this Cartesian system, you know, so here is plus X. Now you see when I change the color, the graphic is gone. This F2, if I write it in the typical X direction, it should go to the right, right? But you should know from the free body diagram that the actual direction should point in the opposite direction of F1. So I can say F2 is equal to minus F1. So I can say here as well that F2 is equal to minus AE over L D1. Right? And don't forget to add the superscript later on, like this, like this, like this. And I can do the same for here. Okay? And I suppose I can do the same again when I look at this. No, it's pretty crooked. Don't like it. Let's redraw it. One moment. If I look at the same, remember, but this time I add the support to the left and I apply F2 here. Okay, and consider, see when I change the color, the graphic is going mad. D2 now with D1 is equal to D1, not I, D1. Let's erase this. D1 equal to 0. Okay. Right now, likewise, I get D2. It's going to be equal to F2 L over AE. And therefore, F2 is equal to AE over L D2. And doing the same thing, you know, this guy is going to be in the opposite, right? So F1 is equal to minus F2, right? And therefore, I can write F1 as minus AE over L D2 as well. So now, you know, if I put things together, I have these relationships right here. The F1, F2, F2, and F1 here. I don't want to change the color anymore because it make the graphic look worse. It should be in red, but you know, I didn't change the color. So we have 4 equations now, okay? So that means from this, I can now write everything in terms of metrics. So let me try to use the good note instead, okay? So now I can form the equation from, we have now F1 of member I equals to AE over, it's not very clear. Would it be better if I change the size of the pen a little bit, like this? Now we have F1 equals AE over L D1. Is it better or is it worse?
Worse.
We have F2 is equal to AE over L D1 minus, then we have F2 equals AE over L D2 and F1 minus AE over L D2. Okay, so I can put this in the matrix form. Okay, now go back to the big one. Try to write big F1 and F2 of member I. Okay, now this, if it's F1, what do we have? It's A E over L and minus AE over L, right? If it's F1, this shall be multiplied by D1 and then D2 of member I, right? And if I do D2 here, it's going to be minus AE over L multiplied by D1 right here, right? And then AE over L. Okay, so I can simplify this by taking AE over L, or right, better, do again, AE over L, and this matrix should be 1, minus 1, minus 1, and 1. So now you can see you can have your stiffness matrix of any member I. Okay, but that's not the end of it. We need to further our stiffness matrix a little bit, because if you can recall, we have done this from this member with degree of freedom in this direction alone, right? But in the real world, you know, you have your two force member, you should have degree of freedom in this direction as well, so that we can now have our member in a complete 2D world. But you should know that the red degree of freedom that I write down here, it's not the direction whereby if you have a force, you will have displacement, because the displacement in the thrust should only be in the direction parallel to the axial, to the axis of the thrust, right? So that means if I add this, and you know, this blue one is F1, D1, F2, D2, right? If I add the third one, F3, D3, and F4, D4, the red ones should be 0. Do you agree with me? Now, for those of you who may not remember the thrust very well, or may not have good fundamental, you will always have, you can always, you know, miscalculate and have F3 and F4 in the thrust. If you have the force perpendicular to the member, those forces will generate moment. Am I right? So that means whenever you have F3 or F4 on your thrust member, it is no longer a thrust member, because this F3 and F4 will generate moment. And therefore, when I expand the matrix by adding the term F3 and F4 to F1 and F2 that we already have, the response should be 0. So we can keep this 1 for F1, minus 1 for F1, minus 1 for F2, and 1 for F2. The rest of the response should be 0. Okay. And the displacement, we have D1, D2, D3, and then D4. Now to complete this, we can always add the superscript I, say, hey, actually, you know, this, we are talking about the stiffness of member I. Displacement and the force on member I. Okay. Now, please look carefully. You know, as my very beloved advisor likes to do very much, you can always change the order of the degree of freedom, you know, the force. Right now, you see, I start things off very easily, try to ease you into the system by say, okay, F1 is in the node 1 in X, F2 is in node 2 in X direction. But this is perhaps not the general notation people like to use. So from this, they generally would love to have something like this, you know. So same member, but in the real world, you tend to see things like this more often than not. They call this F1, D1 like this, but this is generally called F2, D2. You know, just get everything over for the first node, and then this becomes F3, D3, and then this becomes F4, D4. So when I change the order like this, how do you think our matrix is going to change? Is it going to change? Oh, absolutely. So this will change into, let me write in the new page for you. So can I, okay, you know what? I see student do this, but I don't know if I can do it. So now what? Cut, right? Actually I can do it too. Paste. So, okay, actually just got a little bit with me. Let's take it out, okay? So from this, we can now have the new way to write our matrix, okay? So it should look like this now. Okay, F1, F2, F3, and F4. This is the force matrix. It's going to be equal to AE over L. And this is part of this stiffness matrix. You have 1, corresponding 1. 2, you don't have anything. 3, it's -1. And then 4, nothing. Right? And in the 2 direction, this one, it should be all 0, 0, 0, 0. And then when it comes out to 3, it's -1, 0, 1, 0, and then 0, 0, 0, and 0. All right. So that, ladies and gentlemen, is the stiffness matrix followed by the displacement matrix, D1, D2, D3, and then D4. So this is more general form that you can find more often than not, okay? And let me complete this by adding the superscript I to everything like this. So, you know, let me emphasize again that this is the stiffness matrix. Okay? Or we can say that this is basically your force matrix equals K stiffness matrix and then D. Okay, the typical equation. All right, but unfortunately, with this alone, we cannot work our problem out. So you need to work with this a little bit more. Okay, now let me try to put a break on here and see if you can catch up. So does anyone have any problem? Still pretty straightforward enough. Okay, and if you have any question, please don't hesitate. All right, just try to you know, adjust yourself and adapt to the current situation. Okay, this is what we have now, and we probably need to have a class like this for the entire semester. Okay, even though we may have the normal final exam. Okay, all right, so this is the typical form of the stiffness matrix, but we cannot go ahead and use that yet, because if I can go back here, you see, we use the typical Cartesian system. So it is okay for a member like this, you know, it's in the typical XY direction. So you can go ahead and identify the unknowns like this, like what we have in this picture, and use the stiffness matrix. So what is going to happen if your member, you know, doesn't lie in the typical XY direction? It's inclined like this one, this one, this one, and that one. And you should see now that for these 4 members, or like this one, and that one, you know, generally, if member is in this direction like that, you know, in Cartesian, you have X and Y, right? But in order to calculate anything relates to this member, you shall need the force and displacement in its own axis. Okay, so any typical XY direction that we refer to, this, you can call this global direction. Okay, a universal XY direction, it's global direction. But you need the XY in the axis of the member. So in this system, we call it local, because it is for one particular member. So it becomes a local system for the local member. So we need to find the relationship between the global axis and then the local axis. So we need to do something else to find the relationship, okay? So you can reverse back to this file. So we have the general development. So we are, you know, this is, you have this matrix already. I already show you in the good note that it begins here. So you can fill this if you want. Oops. By, you know, that's this typical is for F1, D1, and then F2, D2, right? And then when we change this to F1, D1, and then F2, D2, this is what you're gonna have. All right, I already show you how it happened, okay? And if it's not clear enough, you can refer back to this supplement. Okay, let's move on to the next page. Now this is it, okay? Now you can see the, you can look at this matrix, you see it now, but you know, let's say I'm gonna try to show you later. But this picture is written more clearly. Now you know the black one here. This is, oops, I shouldn't be writing it here. This is the global, right? So when I superimpose the black ones onto the node, you see, this is a global, where, you know, it cannot be used directly to calculate anything if you have the force and displacement in this direction. We need it in the blue and red, which is local. Ah, it again. Hate this. And now it's not coming back. Oh, damn it. Okay. It's the black one. Okay, global. All right. Sorry for the mess. But you need the local one. Okay. The local, you have this in X direction, and you have this in y direction. We're going to need that, so I'm going to reverse back to my good note with this picture in mind, okay? And again, let me try to say, write down a few more things here. We are going to identify this. Let's say if this is the member, okay? That's the member. So we're going to call this angle theta, okay? And this is node number 1. That is node number 2. So I may call this with, because it's global, so I'm going to call this capital D1. Okay, and that becomes capital D2. Okay, now we're going to use the general term now. So 1 and 2 is in node 1. And so this becomes D3, and that becomes D4. All right, guys? And we are going to try to change things into the local node, or may I write in black as well, so that if I don't have to change the color back and forth and ruin the graphics, okay? So I'm gonna try to turn the global values into the local ones, which is D1, D2, D3, and then D4. Okay. So all right, I'm gonna back to my good note now. You can see the picture. So from that, with this picture, with the global D1, D2, D3, and D4 into, let's use the black one. Okay, and this is D1. Oh, actually, yeah, okay, that's fine, that's better. D3, D2, and then D4, okay? So if I superimpose that, you should see that my D1, this is our angle, right? D1 is going to be equal to, if that's the angle, that's the angle. It's capital D1 cosine theta, right? This D1, see that, right? I'm painting it now. Cosine this angle. Okay, and then D2 is going up here. So it's plus D2, if that's angle, this is the angle, right? So it's going in this direction, so it's sine theta. Okay, so that's D1. So we can do the same with D2. For D2, you can guess it's going to be minus D1 sine theta plus D2 cosine theta. Right? D2 is this one now. So D2 is, this is D1. So I'm making this D1 into this. So it is sine, but it's in the opposite direction. So because D1 is coming in here now, so it becomes minus D1 sine. And then we want D2 in this. D2 is in that. So D2 now move to this. So it's cosine, right? So that's your D2. And likewise, it's the same for D3 and then D4. D3 is in the same form as D1, but we change into capital D3 instead. Ooh, good handwriting. So this is D3 cosine theta plus D4 sine theta. and then D4 is minus D3 sine theta in the same form as D2 plus D4 cosine theta. Okay, now I can write this in this term as well. So I don't know if you prefer me to write it again, but if I put this in the matrix form, this is what you're going to get. There. Okay. It has a name. This is what we call the transformation matrix. Some call it T. Some call it lambda. Okay, I guess I'm just gonna call it lambda. I don't know why, but yeah, kind of a personal preference. Okay. Now, since cosine and sine are pretty long, so we can start writing cosine by C and sine by S. Okay. Now, before we move forward, this transformation matrix has a one very important property, that is the transpose of the matrix is equal to its inverse. Okay, so you can say lambda T is equal to lambda inverse. It means you can just transpose it and you get the inverse, right? Isn't that cool? Very cool. Okay, but now we have the transformation matrix. We have the stiffness matrix in the global direction. So now we're going to make use of the transformation matrix and the stiffness matrix and try to create the system whereby you can use to solve any problem in the global direction. Okay, it is 10:20 now. If I begin there, it's going to take a long time and your break will be late. So let me cut it short here and try to stop the record. Okay. Stop record.